Can you see my screen?
Yes.
So this is the theorem we are going to prove today. All right. So here it is. Let me state in other terms, which will be actually useful later as well. What's going on? This is given. Yeah. Sorry for this interruption. My tab is not working. Let me tie it up with the USB cable. Hope this will work now. Yeah, it's fine. Today is 19. All right, so we want to state first this theorem in a different context. So this is in terms of the function, property of the function instead of property of the graph. So let me just write it. Theorem. So f is let f from AB to R be a continuous function or be a function, whatever I write, continuous. And continuous function such that f has second derivatives on AB, then yeah, we don't want to write graph is convex downward. We would like to write f is convex. Convex is a kind of very standard terminology, and it is true in high dimension as well. And the notion of convexity plays a very important role in high dimension. If is convex, and this is a very important theorem which has multivariable generalization. Is convex if and only if If double dot x is greater than equal to 0 for all x, maybe. So what does convexity means? It means the value of the middle points is less than or equal to the value of the chord joining the 2 points. Right? So here it is the picture. Suppose this is x-axis, this is x-axis, this is y-axis, and A, B. So for any 2 point you take between A and B, the chord joining here must lie upside. That is the definition of convexity, and which actually would actually imply, you see, convex upward at every point. So ultimately, that when you take this x and y, these 2 points, x1 and x2 goes to a certain point, this chord becomes tangent, and so curve lies on the top of the tangent. Look. All right. So how should we go towards the proof? Any idea? Suppose suppose f is convex, which means on let's say AB, that means for every 2 points x1, x2 in AB, f of tx, tx1 plus 1 minus t x2 is less or equal to t f of x1 plus 1 minus t f of x2. So the value of the function is less or equal to the the value of the function, chordal function. So this chord function at the chord. So anyway, so this is true. Now what we want to do, we want to do a little bit experiment like this. So suppose this is x-axis, y-axis, and suppose this is A and this is here B. And suppose let's look at a point here x, and let's look at a small a point in a neighborhood of x. Let's look at x plus h. Let's look at another point x plus 2h, right? And let us look at this one, the values, corresponding values here, here. Right, you see, so let x belongs to AB, right? Then choose h sufficiently small such that x plus 2h belongs to AB. Alright? Now you see x plus h is nothing but x plus x plus 2h by 2. Ah, right? So t is half here. So half x plus half x plus h, right? And now we can use this one. So using 1, we get that.
Sir,
Yes,
so in the previous line, it will be half x plus 2h, isn't it?
x plus.
2h, isn't it?
No, see here, x is a point here. This x is a point and x plus 2h is a point.
So one half of x plus 2h, isn't it?
No, we want to write in this form tx1 plus 1 minus tx2. So x1 is x and x1 is x. So this is x1 and this is
Hmm.
x2,
So
right?
in the next line, half x plus half of x plus 2h. That's
Yeah, this is gotcha. Yeah. Right.
yeah.
Thanks. This is 2h. Yeah,
Hmm.
sure. Thanks. So now we get f of x plus h is less or equal to half of fx plus half of f of x plus 2h, right? So this implies to this simple exercise here. So this is fx plus f of x plus 2h. This implies f of x plus h minus fx is less or equal to, I mean, here we choose h sufficiently small, of course, and of course, and h, you want h, let's take h greater than 0. And this is f of x plus 2h minus f of x plus h. Oh, do I need h greater than 0? Maybe not. Maybe not. H may be less than 0. Don't worry. Yeah, that is not required. That is not required. True. Yes. All right. So you see here, this is true. Uh, Now the point is here. See. So now, so if x plus 3h belongs to AB, same this one, then we have by following the same procedure as above, that f of x plus h minus fx less or equal to f of x plus 2h minus f of x plus h less or equal to f of x plus 3h minus f of x plus 2h. Right? Do you agree with this? So if x plus 3h is also there, then we can prove this one. Do you agree with this?
Yes, sir.
Right. So x plus h will lie, I mean x plus 2h will lie in the middle of x plus h and x plus 3h. Right? And that will give you this one. All right. So now what we do is we do some basic stuff. So which is choose, you know, choose 2 points x1, x2 in AB such that x1 is less than x2. All right. So we have this x1 This is AB, this is A, here is B, and we choose 2 points x1 and x2. And what do we want? We want to divide this interval x1, x2 by smaller intervals, right? So divide, let h be x2 minus x1 by n. N fix, n belongs to n. If large enough, we don't mind actually. We want to take large enough, n tends to infinity, but this is true for any age, as well as this, all these things, all this x1 plus h, x1 plus 2h, all this lies inside AB, right? Now this is h. So by 2 actually, repeating 2, we get that f of x1, see here minus x, so x, we have started with x. So here, this is x1 plus h minus f of x1, we will start with x1. So less or equal to f of x1 plus 2h minus, what happened? F x1 minus plus 2h minus f of x1 plus h less or equal to f of x1 plus 3h minus f of x1 plus 2h. And so we can continue this until where? F of, see here, in the end it will be the end point. So let me write the last term, then I'll write the previous, um, yeah, the term before it. So last term will be f of x2, which is x1 plus nh, which is x1 plus nh, right? Minus f of x1 plus n minus 1h, which is x2 minus h, which is x2 minus h, right? And that will be this f of x2 minus h minus f of x2 minus 2h. All right? Do you agree with this? So this is n. This is not h times h. This is n. Do you agree with this one? So what we did, we divide each term and we consider 3 together, and then this 3 together. No, sorry, this 3 together, and then this 3 together, and then this 3 together, and so on. Right? Then we get each of the inequalities. Yeah? Now from here, f of x1 plus h minus f of x1 by h is less or equal to f of x2. We will go actually up to x2 plus h. All right. So we will go a little bit more here. So this is x2 plus h to make things proper. So this would be f of x2 plus h minus f of x2. Right? So if we go up to x2 plus h. so that x2 plus h belongs there. So this is x2 plus h minus f of x2 by h. We can do that, right? Is this clear?
Yes, sir.
So what we'll do next? What will you do next?
Take the
Limit
limit.
of e is going to 0.
Right. Take h tends to 0, which means take n tends to infinity, which means take h tends to 0. So this gives us f prime x1 less or equal to f prime x2. So what we get is f prime is monotonically increasing, right? On AB. Yeah. For every 2 point x1 less than x2, you get this one. X1 less than equal to x2, you get this one. Actually, you can take less than equal to x2. If x1 is equal to x2, there is no problem. So less than x2 matters. Yeah, so monotonically increasing. What does it imply about the second derivative?
Positive.
Yeah, non-negative.
Yes, non-negative.
F prime x is greater than equal to 0 for all x in AB. Right, when greater than 0 is strictly increasing, we have told the same procedure by using mean value theorem. You can see that this is greater equal to 0. Monotonically increasing implies this. Right? So one part is done. So suppose, conversely, suppose f double prime x greater equal to 0 for all x belongs to AB. Right? What do you want to show? We want to show f is convex, right? Which means f of yeah, f of, for any 2 points x1 x2 in AB, actually in AB, f of x1 f of tx1 plus 1 minus t x2 is less or equal to t f of x1 plus 1 minus t f of x2. Right? All right. So how do you proceed?
Taylor expansion.
Taylor expansion, right? So we'll look at Taylor expansion, but you need to define another function, the chord one. Okay. So the point is here. Y. So this is, let's say, A and this is B, x1 and x2. So in that interval, we want to define first this function, this function. Okay. So you want to. So what is this function? So what is the coordinate of this point? This point is x comma x1 comma f of x1. And what is this point? x2 comma f of x2. Right? Now what is this function? I want to write this as a function fx, let's say. Uh, yeah, so what is this? This is coordinate geometry, right? What is the equation of the line joining these two?
X minus x1 by x2 minus x1 equal to y minus fx1 by fx2 minus fx1.
Right. So we want to find y, right? So define alpha x to be y, right? So what would be the y? Y will be
Why not?
fx1, right? Y minus y1 plus fx2 minus fx1 by huh? x2 minus x1, whatever. I mean, if you put fx1 minus fx2 by x1 minus x2, that is also fine. And here x minus x1, right? Is this correct?
Yes.
Yeah. So y minus y1 is this y1 minus y2 by x2 minus x1. I would say y2 minus y1 by x2 minus x1. ক্লাস চলছে একটু পড়া যাবে? আচ্ছা রেখে দিন। থ্যাংক ইউ। Yes. Okay, so we want to define, sorry for this disturbance. We want to define alpha x is this one, the equation of the line. Now define another function, define, and we actually want to look at the difference between these two. So define define capital Fx to be small fx minus alpha x. Alright? The difference between these two. What we want is, we want to show fx is capital Fx is less or equal to 0 for all x in x1, x2, right? So that will prove our theorem, right? Is this okay? So x is actually the point t x1 plus 1 minus t x2. All right? And this is the equation of this line is just t f of x1 plus 1 minus t f of x2. If you parameterize it, if you written another way, it is this. All right? So this one, we want to prove this one, which means this is a point x here. So this is fx and this is alpha x for this x. Do you see it? Yeah? Is this clear?
Yes, sir.
All right. Yeah, so this is another way of writing this one, same thing. All right, suppose not. Suppose there exists a point, let's say what, x naught, such that fx naught is greater than 0, right? So now if you look at supremum of fx on x1, x2 is attains at some point in the interval, open interval x1, x2, because we know f of x1. So here, why is that so? Because f of x1, which is fx1 minus alpha x1. So what is it? X equal to x1, this is 0, right? So alpha x1 is equal to f of x1. So this is 0, which is again, this is f of x2, which is clear, right? So if x1 and x2 at the end point, the value of this function and value of this function are same, right? That's what is the construction, right? So that gives you 0, but here one point you get greater than 0. So this attains at some point inside. So without loss of generality, we may assume that f of x naught is the supremum. So this x naught point, we don't want to bring another point. This. You can assume this, rename this x naught to be the points where it attains the supremum. So here nothing but rename the point at which max attains as x naught. There is nothing else here. All right. So here you have supremum attains, and see f is a differentiable function, right? Function on whole of AB, so on AB actually, on here also. Let me, what is our concern is between x1 and x2. So on x1 a comma x2. So this implies f prime x naught is equal to 0, right? Do you remember the theorem? F is differentiable if attains maximum at x naught, implies the derivative is 0. That is very important theorem of this chapter. Do you remember those? That theorem?
Yes, sir.
All right. So what does this gives? What is the derivative of fx naught? So this implies fx was up f small fx minus alpha x. So this means f prime x naught is equal to alpha prime x naught, right? So what is alpha prime x naught? Alpha x is this one. So this fx1 is constant. This, the whole thing is constant, right? And here x minus x1 is there. So x will contribute to the derivative. So this derivative will be this one. Fx2 minus fx1 by x2 minus x1. Right? Is this fine? Now we use Taylor's formula. We now use Taylor's formula for capital F at x naught. So f of x naught up to, of course, second derivative exists. So we'll go, the remainder term will be consisting of second derivative. So f of x naught, sorry, f of x will be capital F x naught plus x minus x naught capital F prime x naught plus x minus x naught square
Excuse
by
me, sir.
yes,
Sir, when we take f dash x naught to be 0, we do it for local maxima or local minima. But if x naught is one of the endpoints, then it is not necessary to be 0, right?
true. But you see, it attains in the mid some point in the open interval.
Oh, okay, sir. Okay, sir.
Yeah, that's what we did some work so that this x naught lies in the middle, not at x1 and x2, right? Because at x1 and x2 it is 0, and there are points where it is greater than 0 in the middle. So maximum will be attained in the middle. All right?
Yes, sir.
Okay. So this fx will be this one, then f of x x naught plus theta times x minus x naught double prime for some theta 0 theta between 0 and 1. All right? Now this part is 0, right? This part is 0 because this is f prime x naught is 0, right? Now this will be f of x naught plus x minus x naught whole square by 2 f double prime x naught plus theta times x minus x naught, right? And this is true for all x in the interval, right? In the whole interval. This is true for all x for some theta, of course, and for all x in the interval x1, x2. Actually, the closed one. We can do a little more because x1, x2 was 2 points inside the open interval AB. So we can actually go till closer. So this implies we evaluate now f of x2. So f of x naught plus x minus x naught square by 2 f double prime x naught plus theta times x2 minus x naught, right? So here let me go to the picture. So x naught is somewhere here, and we are looking at this interval for the next here, right? Now what is f of x naught? F of x2, this is 0. But this one is greater than 0. This one is a quadratic term. This is x2. And x2 is not equal to x naught. So this is greater than 0. And by assumption, this is also greater than 0. So this is a contradiction, right? So one side is equal to 0, other side is greater than 0. That gives you a contradiction. So this implies f of x has to be less or equal to 0 for all x in x1, x2, right? And this is the proof. This proves the theorem. All right. So one topic is left out is which is Lopital rule. So Lopital rule, all of you know. I'll give a note because the proof doesn't have anything uh, particularly important. It's just technical only, nothing, no new ideas as such. So I'll not present here. I'll give a note. But I can tell a story about this L'Hopital's rule, how it becomes L'Hopital, right? It's actually Johann Bernoulli who proved it. Okay, and he used to give tuition to L'Hopital. So, well, then L'Hopital learned from him, and then he paid a lot of money so that he can actually publish the results which he had learned. That's how it became L'Hopital's rule. Yeah, later people have found it that it is actually from Bernoulli's work. All right, so next topic is, it's also very interesting. So L'Hopital rule, I'll give note. I'll not give proof here. So existence. So this is very interesting. Existence of continuous nowhere differentiable function. So what do you mean? So this is to find a function which is continuous in whole of R but differentiable at no point. And these functions are quite big. I mean, class of functions of this kinds are quite big. Okay, so we'll not give existence. Of course, the existence will be proved. We'll give an example. Example that will definitely prove the existence, but it's actually a huge class. All right. So the first one, the first example was given by Westrus in 1872. So let me give you what he actually proved. So his example was fx. So this is Westrus example. Example. Fx is summation n from 0 to infinity a to the power n cos b to the power n pi x. So infinite series plays a role here where 0 less than a less than 1 and b b is a positive odd integer such that AB is greater than 1 plus 3 pi by 2. That was given by Weierstrass. Then actually people have, for example, A equal to 2, A equal to half and B equal to 7, A equal to half and B equal to 7 what works here. Then later on, people have actually constructed different examples. Uh, so what I'm going to prove, what example I'm going to give is actually by routine. So maybe let me mention one thing, one example, similar type of example by Hardy. This is n equal to 1 to infinity sine n square pi x by n square. So this is by Hardy. And third one which I'm going to give is by Rudin, which is in his book. So this one you can try proving this. So the part continuity is very clear because this all the series are uniformly convergent. So there will be no problem in continuity. To check the differentiability is the task, which is a bit difficult. Okay. What Rudin takes is he does a very simple trick using this phi x to be mod x. Okay. On let's say on nowhere minus 1 less or equal to x less or equal to 1. So at which point it is not differentiable?
0.
Right, it is not differentiable at 0. So he want to build it right there. So this function was something like so this is minus 1, this is 1. Sorry, it's not like this. So right. Okay, so he actually right, right. So he defined something like this. Now what he said is extend this function continuously to whole of r by putting this f of I of x plus 2 is phi of x, right? So your value here is same as value here, which should be value same value here would be same value here, same value here would be same value here, something like that. So at one it would be continuous, so it will be something like this, same type of thing. So extension will be something like this. This is 2. So 0 and 2 will have the same value. Something like that. And similar here. Okay. You see this condition means like this. This will have the same value. This will have the same value as well. Right? So x plus 2 is equal to phi of x. Now define a function fx, so f from R to R. So fx is summation. Again, the series will be coming n from 0 to infinity, 3 by 4 to the power n phi 4 to the power n x. Okay. Now you see, since 0 less or equal to phi x less or equal to 1 for all x in R, the series in the RHS converges uniformly on R. And if you look at finite sum, that is a continuous function because it is like mod x, right? If you look at finite interval, this is finite sum, it will always be continuous. So the limit of uniform limit of continuous function is continuous. So this implies f is continuous on whole of R. So the only thing is differentiability. So since we don't have time, we just sketch what to do. We need to find, so to show f is not differentiable at every point x in R, we we fix we fix x in R, and we we so there exists a sequence yn or xn such that xn converges to x, but well, sequence, let's say hn hn. So hn converges to 0, 0, but uh, f of x plus hn minus f of x by hn. Right, it actually what to do? It does not. Well, at some point it will be 0, so does not exist. Something like that. So this is what we need to show. So what do you? I'm giving you this scheme. So you choose. We have already chosen x, and now choose m in n and hm to be 1 over 2 times 4 to the power n. Okay, or minus 1 over 2 to the power n, 2 times 4 to the power n, something like that, either plus or minus, depending on that, such that x plus uh, 4 time, so such that, so choose this one, choose this thing such that, actually choose hn such that uh, 4 time 4 to the power n x, and the interval 4 to the power m x joining 4 to the power mx plus hm does not contain any integer. So do this one. So taking this one would work actually. Then calculate calculate f of x plus del x plus hm minus fx by hm. This calculate and I'll see what happens. Okay. So to complete this proof, exercise that this is not differentiable. So complete this proof. Okay, so if you don't get, so let me know next time, then we'll prove. Otherwise, from next time onward, we'll start integration.
Sir,
Yes.
is it possible to construct such functions without using infinite series?
Yeah, that part, without using that part, I don't know, and most probably it's not. You have to go to some limit somewhere.
So basically, the idea is extending one non-differentiable point into infinite non-differentiable point by using an infinite process.
Right, using an infinite process. A sequence of points, which actually at each step you'll be increasing finitely many, and ultimately you will get
Hmm.
everyone.
Hmm. Hmm. Okay,
Yeah,
sir.
that is actually the idea. Yeah, and then if you go to the Wikipedia page, you will see actually the function how it looks. So let me give a search and show it to you. Uh, a nice animation is there. So, yeah, so this one. Right, it's something like that. If you zoom it up at this point, it will be again like this. Yeah, I saw your animation over there. I don't know, it's not giving me now. So the graph would be something like this. So of course here we have constructed at 0 it is 1, but they have constructed at 0 it is 2. Okay, the difference is nothing but that. And then at each step one just look at this one. So a lot of peaks. At every point, a lot of peaks. That's the idea. Okay, do you have any question? Okay then, so we'll see you next time.